As I've already told you, tomorrow my wife and I take off for Ho Chi Minh City, spend some time with her wonderful family. And during that period of time, Andrew Mosen will present the lessons. After we finish our talk today, I'll give you back exam 1. The scores are now posted to Sakai. When I return the papers, I'll make some comments about such. All right. Let's proceed with Chapter 18. If possible, wrap it up so that Mr. Mosen can tee off with Chapter 19. But if not, I'm sure he'll finish this with no difficulty. To wrap up our conversation on the 10th molar aluminum sulfate solution, let's report it to 2 sig figs. Write again the complete species charge balance equation, which we did previously, and ask if 0.60, which maybe we did, but won't hurt to talk about it again, if 0.60 is the legitimate charge sum for this charge balance equation. Any arguments? Any comments?
Could you simplify it on the
Wait, let's not do this. Let's talk about this. Then we'll do this.
Yes.
The answer is yes. Why is 0.60 legitimate charge sum for this charge balance equation, complete species? We looked at the principal Bronsted-Lowry acid-base equilibrium reaction in this system. Remember what it is? This thing, which represents aluminum with 6 waters of hydration, charge of +3, reacting with sulfate ion, because that aluminum ion species is the main acid in the system, and sulfate ion is the main base. But we recognized that the products for that reaction, hydrogen sulfate ion and the conjugate base of Al3 plus, quote unquote, which is Al2 plus, quote unquote, are respectively stronger acid, stronger base than the reacting acid. And when you compare the Ka values, hydrogen sulfate ion 1.2 times 10 to the minus 2, the Ka hydrated aluminum ion 1.4 times 10 to the minus 5, product acid is a good deal stronger. So what's that tell you about reaction extent? It's got to be considered if you want to calculate the hydrogen sulfate ion molarity, but the reaction extent is still nevertheless pretty small. So that means the sulfate ion molarity in the system is practically speaking the same as it is initially. And what is the initial sulfate ion molarity? For this system, 0.30. But in writing the charge balance equation, we have to double the sulfate ion molarity, so this becomes 0.60. And if we have just recognized, which I hope we have, that sulfate ion isn't really going anyplace else, it doesn't convert to any significant or appreciable extent to become hydrogen sulfate ion, well, then that value remains intact, so this is valid. If we wanted to tackle this relationship, say, for example, to get at the hydronium ion molarity, do we have to pay attention to every term? Could we simplify? Could we eliminate some of the terms? What considerations would you make to respond to this consideration? This an acidic solution? Is it a fairly acidic solution? Did you, for example, note that Ka for hydrated aluminum ion is about the same as Ka for acetic acid? That's the base table tells you that. K acetic acid 1.8 times 10 to the minus 5 for our quote-unquote Al plus 3, 1.4 times 10 to the minus 5. 10th molar acetic acid solution. I asked that simply because we've done a lot of arithmetic, a lot of analysis for acetic acid solutions. Remember what kind of gee whiz pH we got for 10th molar acetic acid solution? In particular, that is a solution that you investigated with your laboratory work, assignment number 1 this term. Anybody remember, gee whiz, what you found to be the pH for that solution? By experiment? You could do it by calculation, of course. You just did this work. Nobody remembers? Why not? I'm curious. You spend 3 hours in lab practically on an assignment and you don't remember any of the information you collected. Why not? You got somebody's lab book from last term? I know daggone well you all have access to laboratory manuals of students who've taken and completed 46L. I can't stop that. That's why I tell the TAs when they're with you folks in laboratory, before they provide any OKs, you have to prove to them you've done the experiments. You have to have the vials and test tubes and beakers and everything on the benchtop containing the experiments and their results when they are coming to you to provide the OK. And if you, for example, don't have this and say, well, I already did the work, but I cleaned up my test tubes and apparatus, that's why I don't have the results. Their job is to say, do it again. That's it. You got to prove to us you're doing this stuff. And you can't learn from it if you don't do it. Acetic acid 10th molar. pH 2.9 if you want it to 1 sig fig on the nose. Roughly 3.0, which is about what you would have gotten with the rather crude but on the money indicator analysis methods that you used. Well then, this solution should have a pH in the vicinity of that, a little bit higher. Well, that means the solution is fairly acidic, doesn't it? Well then, is this going to have a value that's appreciable? No. Now then, let's draw a comparison of this solution to the iron nitrate solution. For the iron nitrate solution, which we'll talk about some more in a moment, has respective Ka1 and Ka2 values of 4.0 times 10 to the minus 3 and 5.0 times 10 to the minus 4. Here, our first Ka value is a good deal smaller than 4.0 times 10 to the minus 3. So Ka2 is certainly smaller than this. We don't expect it to be a lot smaller because this, like iron, is a hydrated metal ion. But this molarity is 10 times greater than the iron nitrate solution. So with the much smaller Ka and the 10 times higher molarity, what do we know about the extent of ionization of aluminum plus 3 in this solution compared to the extent of ionization of iron plus 3 in this solution? Silence is deafening. What does the extent of ionization depend on? How many times have we mentioned this? Magnitude of Ka and the dilution factor. Well, the solution is 10 times more concentrated. That means a smaller ionization extent. And Ka a lot smaller. That too means a smaller ionization extent. So what does that tell us about the likely molarity of this thing? Appreciable? Probably not. You got to think about these numbers. You got to let this stuff talk to you. I mean, science is forever dealing with these numerical quantities, and you got to know what these things mean. If you look at them just as numbers, you're going to be forever perplexed in any science class. From Chad, I was overhearing while I was writing notes on the board. I suspect some of you are in physics. They deal with numbers in physics? Calculations? How many of you in physics? Okay. Well, just a few, but hey. So we can probably forget this. I mean, to know absolutely and for sure, you have to do a calculation. But I'm betting you can probably forget this. I'm just talking about the things which, for a system like this, you should think about before you start doing any calculations. Give yourself an idea what you're looking for before you start looking. Back to the iron nitrate solution. You see, before I finish and go to this, the hardest thing I should think about what's going on here compared to what you've done in previous chemistry is, in the past, you're always looking for some kind of an absolute answer with no decision making to be made. No science is like that. I have this discussion with my 2045 teaching colleagues all the time. You're not asking these people to think. And when they come to me in 2046 and everything is based on thinking, they're in big trouble. I don't want you to be in trouble. Well, we got to get past this. You got to open up the mind and think. Any endeavor of consequence in life, I don't care if it's science or not science, is going to require this on your part. You got to think. At least if you're interested in getting some kind of job of responsibility and importance. And my belief is you wouldn't be in university if you didn't have that in mind. Hey, I want you to get the most out of this. And although few of you will likely do anything in particular with the chemistry that we talk about, if I can sharpen your abilities to analyze a problem, to think more sharply and clearly, hey, then we're doing you a lot of good. Because that's what the heck university is supposed to do. I got a feeling you know this. The unfortunate part of this is you may not yet have been in a class which in fact required you to do this. But you are now. You know that. Well, enough sermon. Let's carry on. For the iron nitrate solution, we recognized, because of the appreciable extent of Ka2 in conjunction with Ka1, when looking at Ka1 and Ka2 alone, we got 4 unknowns and 2 equations. So we had to develop at least 2 more simultaneous independent equations consisting of the same set of unknowns in order to solve such. This you learned in algebra class back when. And the additional equations were material balance and charge balance. So with the material balance and charge balance equations, in addition to Ka1 and Ka2, we can solve for this solution for the hydronium ion molarity and the molarity of any other species in the system should we be interested in doing such. Now, let's talk a little bit about what we would do to get at the solving. Number one, would you expect the ionization extent, since we have so far said when we got one of these solutions to wrestle with and you're looking at a quadratic or some such equation to solve, we said think about it, approach it from an ionization extent standpoint. So you get a feeling for chemistry. You start to get an idea of how a Ka value and a molarity will relate to ionization extent. You think the ionization extent for this reaction before it comes to equilibrium will be appreciable in this system? This is small. And as far as weak acids are concerned, this is a pretty large Ka value. So together, these considerations tell you what about gee whiz ionization extent for this reaction? Significant, appreciable? You're daggone right. All right? Now, if this thing went 100%, we'd have a hydronium ion molarity of 0.010. Well, if this went 100%, then of course we'd have to focus on the second ionization to in fact get the hydronium ion molarity. And if the second ionization went 100%, these of course are not possible. But nevertheless, we know the second ionization is appreciable. What would be the maximum hydronium ion molarity based on the first and second ionization? You see the second ionization reaction in your noggin? Or you can look at your notes or the chem notes. Fe+2 reacts with water to make hydronium ion and Fe+. If that too went 100%, what hydronium ion molarity would you wind up with? Nobody got an idea?
0.01.
No, you got that from the first ionization.
0.20.
0.020. Well, we know these are equilibrium systems. They're not going to go 100%. But that would give us a handle on maximum possible hydronium ion concentration for this system. We'll put this in. And as we have also done previously, for hydronium ion calculation, if possible, we like to put this hydronium ion concentration in a box. It goes back to what we did at the end of chapter 17 when we looked at the ammonia and hydrogen and nitrogen equilibrium reaction and recognized that the algebra expression we developed for that system, if expanded, would give fourth order X. Hey, trying to solve that with rigorous algebra, you're going to have a fit. Well, we found it was easy to solve. We did so by putting X in a box. I'm going to do the same thing here, except that here X is the hydronium ion concentration. So I am saying that if I want to get a minimum value for the hydronium ion concentration, to this first ionization equilibrium, I'll apply x squared over m sub I minus x. Why does this give me a minimum hydronium ion concentration? Does this expression in fact apply legitimately to this? Yes or no? Remember what x represents here in the numerator. It's the molarity of this and the molarity of this. If I treat this with x squared over m sub I minus x. Is it true for this system that the equilibrium molarity of this and equilibrium molarity of this are equal? Because if that's true, then the second ionization didn't go in any place. And this would correctly calculate the hydronium ion molarity for the system. That applies if I'm dealing with a polyprotic acid that is weak and molecular. This acid is weak, but it ain't molecular. The Ka values, 1 and 2, are both appreciable numbers. Going back to what we've already recognized, you've got to look at Ka2 to get the hydronium ion concentration calculated correctly for this system. That's why doing the arithmetic for this system, the analysis for this system, is a heck of a lot more difficult than the weak acid system. That's why we had to develop more equations. Because this does not legitimately apply to this. But if I apply this to this, it'll give me a minimum value for the hydronium ion concentration. Because this is saying the hydronium ion for this system only comes from the first reaction. I already know that it comes also from the second reaction. So if I calculate the hydronium ion concentration contributed to the system based strictly on the first reaction, I'm getting the minimum possible value for the hydronium ion concentration. I will know the hydronium ion concentration, whatever it is bigger than the number I get by applying this. And when I apply this, I get 4.6 times 10 to minus 3. If you want, I'll write that as a decimal fraction. And why do I make a point of this? Hey, in analytical chemistry class, well, I don't know. Let me ask. How many of you are going to go to analytical chemistry class? How many are going to go to organic chemistry class? Okay. Well, I don't know about organic, but in analytical chemistry class, you can do problems like this all the time. And I like it when my students go into these classes and the instructor comes up with stuff like this and you all sit there and say, I know how to do this. Hey, one of the main purposes of this class is to build foundation for you to proceed successfully to what comes hereafter. I want that. I want you to be successful. But you got to do your part. And I know after looking at the scores for exam 1, a lot of you folks aren't doing your part, at least not yet. We'll talk more about that later. Let's get on with this. So guess what? We've now determined that the hydronium ion concentration for this solution is not going to be bigger than this, but it is going to be bigger than this. Hey, that's a pretty small box. It's in the range 4.6 times 10 to the minus 3 to 2.0 times 10 to the minus 2. There aren't many data points inside that box, because we're, number one, limited to 2 sig figs. So now you got an idea what kind of number you're actually looking for when you proceed to tackle this in greater rigor so that you get the actual hydronium ion concentration. Now for this system, you now know how to calculate the hydronium ion concentration. It will, of course, take some more arithmetic. I'm not going to proceed with that. You can proceed with that on your own. It's a question which to calculate the true hydronium ion concentration. I would never ask you on an exam, but I'd be perfectly happy to ask you that on a bonus quiz where you got all the time in the world to work on it. But what matters is not getting the answer. What matters for this case is knowing how to get the answer and knowing the chemistry that underlies getting the answer. That's what we've been talking about. That's what counts. That's where the understanding is. The brute force arithmetic that you would do hereafter is not providing any greater degree of enlightenment on this problem. It's like learning how to paint. I mean, after you know how to paint, you've done the hard work. And then you get out with the tedious work. That means get the can of paint and start slapping it on the wall. But if you ever observed what a wall looks like when it's been painted by somebody who doesn't know how to paint, you understand what I'm talking about. Looks like hell. I mean, anybody can take paint and put it on a wall. That doesn't mean it's done properly. Well, you got to get past this. I got the right answer stuff. I mean, if you got a fly on the wall at home, I don't know about you, but I don't like flies on my walls. You want to get rid of the fly. If you own a bazooka, would you load it up and go, wham! Ah, the fly is gone. So is the wall. Is that okay? The boss says, sweep the floor. You get out an eyelash brush. Can you sweep the floor like that? You're damn right. Can you paint the wall with a toothbrush? You're damn right. But I'm telling you what, if I'm paying you to do a job and you're charging by the hour and I see you're painting my wall with a toothbrush, I'm throwing you out so hard and so fast you won't know what the hell happened when you smack into the tree that I throw you into. You're not approaching the problem the right way. Can you get the answer? Yes. But the way you got the answer is not acceptable. And I know you know that when you get into what people call the real world, this is the kind of stuff you're going to have to wrestle with. Well, I got news for those people. This world is just as real as any other daggone world. And in many cases, a hell of a lot more important. Because here is where, if we do our jobs properly, we will make you ready to go tackle these tasks that you will be faced with in life hereafter. That's what I want. You to do this successfully. But you got to do your part. If you don't, well then, you're not going to get the benefits that are available for you. All right, on we go. Page 1846. More on chart sum. Clearly, if we're looking for numbers, like I want to get a hydronium ion concentration for a solution, and I need a charge balance equation for the solution in question, if I can set that equal to a charge sum, that is leading me directly to a possible solution. But in some cases, for some systems, like the system we're going to look at here in just a moment, it is not possible to write a charge sum directly for a charge balance equation. Because the charge sum does not follow from the chemistry of the species that are in the system. The charge sum cannot be written directly from the M sub I numerical label on the bottle. Now look at the systems we have so far considered. Oh, I took that one away. 10th molar aluminum sulfate solution. Charge sum 0.60. That follows from the label on the bottle and from what we knew about the chemistry of sulfate ion in the system. The iron nitrate solution, that's even a simpler case than the aluminum sulfate solution. Why is this even a simpler case when it comes to writing a charge sum?
Because NO3 will not have any additional chemistry once in the solution, while the
nitrate ion is a main charged species in this system. It has a molarity of 0.030, and nitrate ion does not participate in any chemistry in this system at all. It goes in the system and watches things happen, like the person who bought the ticket to go watch the Gators. But daggone it, it's there, and it's part of the charge balance equation, which we already wrote for this system. And it has a value of 0.030. So there's the charge sum. Now then, how about this system? Let's imagine we have the task of calculating the hydronium ion molarity for 10th molar to 2 significant figures ammonium cyanide solution. Well, as I trust by now you know, when you're going to deal with any chemical system, what's the first thing you do all the time? PSI. Pay attention to what's in the system. If you don't know that, then You can't do anything with it. So this stuff starts with an initial molarity of ammonium ion of 0.10 molar, initial molarity of cyanide ion of 0.10 molar, and the mole quantities of these ions initially will depend on the volume of this system. But in order to get a hydronium ion concentration, clearly we have to pay attention to acid-base chemistry which exists in this system. And when we look at our inventory, we see ammonium ion is the best acid, strongest acid in appreciable molarity. Cyanide ion, strongest base in appreciable molarity. So the principal acid-base equilibrium in this system is ammonium ion plus cyanide ion. Remember the aluminum sulfate solution? Principal acid-base equilibrium was hydrated aluminum ion with sulfate ion. For the iron nitrate solution, the principal acid-base equilibrium is the one we got on the board. Now, what's the problem created by this ionization reaction? Well, first the obvious. It doesn't give us a handle on hydronium ion, does it? Because it doesn't involve hydronium ion or hydroxide ion. So certainly for this system, if I want to get hydronium ion molarity, I've got to look someplace else. I've got to look at other chemistry which involves the principal species in the system. But back to the issue of being able to set the charge balance equation. Here it is for this system. Simple charge balance equation equal to a charge sum. Can I do that for this system? The answer is no dice. I wrote that over there. Oh, no, I didn't. Pardon me. Let's write this over here. Can't be determined from M sub I info or M sub I for initial principal species. Well, we recognize that beside water, the principal species are ammonium ion and cyanide ion. We wrote the reaction equation involving these two species. Because this is the strongest acid, high concentration in the system. Cyanide ion is the strongest base and high concentration in the system. And now do you see the difficulty when it comes to charge sum? When these two react with each other, what kind of species are produced? Ions or molecules? Molecules. They don't have charge. And this is the principal reaction involving the main ions of this system. So what's this doing to total charge in the system? As this reaction, right here, as this reaction goes left to right, what impact does this reaction have on total charge in the system? Decreasing total charge. It's converting charged particles to non-charged particles. That leads to a problem. Specifically, for starters, for this charge balance equation, I cannot write a charge sum. I can only write a charge sum if I know to what extent this reaction proceeds. So that after it proceeds, I will know what the remaining molarity is for ammonium ion, the equilibrium molarity. So that I will know what the remaining molarity, the equilibrium molarity for cyanide ion is. And until I know those, I can't set this equal to a charge sum. So, I mean, it's a case where you pay attention to what chemistry is shown to you by the species of the system. You always have to do that. Now then, solving this for the hydronium ion concentration is particularly challenging. When I wrote this part of the notes, I didn't realize that. Hey, I think I told you. For me, from a selfish standpoint, the best thing I get from doing this class term in and term out is every time I do it, I learn more. This chemistry stuff is tough stuff. I get a kick out of these textbook representatives. The salespeople who come around trying to get us to adopt a particular textbook. Or you see this stuff on the web all the time for these online learning systems for general chemistry. With this, you can master chemistry. There's nobody in this world who has mastered chemistry. The best chemist in the world has not mastered chemistry and never will. There's too damn much. These people have a lot of nerve to come after you with these rotten, lousy, lying advertising pitches. You're going to be able to master chemistry after you've used this program. What baloney! I'd like to horsewhip those people. In public. I mean it. I'll take the whip and I'll hit them right before your eyes. Because I'm sick and tired of people like that conning you. And that's what they're doing. Because what they're really interested in is selling you a product which isn't worth anything. They want your money and they don't give a damn how they get it. And I don't like that. And I hope you don't like it either. Especially when it's your money that's being taken away if you purchase this stuff. Junk. The problem with solving this thing to get the actual hydronium ion concentration that I failed to see when I first wrote these notes is I thought that this reaction will result in producing an HCN molarity and an ammonia molarity which are equal. Because that's what the stoichiometry of this reaction indicates. There's no question that this reaction as it proceeds, for every mole of this that it makes a mole of this. That's true. But does that mean the equilibrium molarity of this equals the equilibrium molarity of that? No. That's what I overlooked. Remember what we said? If you want to get the hydronium ion concentration for this solution, at the minimum you've got to go past this equilibrium, because this equilibrium does not involve hydronium ion or hydroxide ion. So, what can I look at? I can look at Ka ammonium ion. I can look at Kb cyanide ion. Now, can I make a gee whiz statement about the extent of this reaction? Look at the acid-base table right now. You know how to get an extent. Strength reacting acid, strength product acid, or for the bases, either one, I don't care. Look at the table. Approx extent equals, we want to replace the question mark with an accurate statement made by you, because you're looking at the data. Let's look at the acids, since that data is immediately available, as opposed to bases where you got to do some arithmetic to get KBs. Ka ammonium ion, 5.6 times 10 to minus 10. See that in the table? Okay. Ka-HCN. Look at the table. 6.2 times 10 to minus 10. Am I saying it correctly? Are these numbers close to each other? You're damn right. 6.2 a little bit bigger. So what does this information tell me about the extent of this reaction? Let's try it this way. If Ka-HCN and Ka ammonium ion were exactly the same, what would be the extent of this reaction? 50%. Well, they're close, but Ka-HCN is a little bit bigger. So what are you going to tell me about the approximate extent of this reaction? Well, I understand less than 50%. 0.000001%, that's less than 50%. Tell me something better than that. On the order of 45%. 45%. I like that. That might not be exactly on the nose, but daggone it, it's going to be close. We know it's close to 50%. So if you wrote less than but close to 50%, hey, that'd be a good statement. So this thing is converting appreciably charged species to uncharged species. That again relates to why you can't set this equal to a charged sum directly. Now back to the issue of the problem encountered in trying to get the hydronium ion concentration. To get the hydronium ion concentration for this system, after I've considered this reaction, I now have how many different reactions could I use to give me a handle on the hydronium ion concentration for this system? How many different reactions? Ka ammonium ion is one of them, or the reaction that corresponds to Ka ammonium ion. Am I not asking you to pay attention to the system species which are principal and which have an impact on hydronium ion? That's what I'm asking you. So could I use Kb cyanide?
Yeah.
Heck yes. We can write that down too. Or Kb cyanide. Or what else? Remember, this thing went close to 50%, didn't it? Mm-hmm. Could I use KaHCN? Yes. You're daggone right. Could I use Kb ammonia? You're daggone right. I can use any of these. They all involve principal system species. And they all give me a handle on pH. The Kb's give me hydroxide ion molarity directly. The Ka's give me hydronium ion molarity directly. Okay? So you can write this stuff down. KaHCN or KbH3N, ammonia. Hey, it'll get me where I want to go. Doesn't make any difference which one of these I deal with. Next question, is this system acidic or basic? Again, before we start doing any number grinding, we want to focus on all the stuff we know qualitatively about the system.
Don't you have to find a KB
Kb for what?
to compare it to the K and see if it's acidic?
Well, Kb for what?
Oh, the KB for ammonia?
Kb for ammonia, that's 1.8 times 10 to the minus 5. How about Kb for cyanide? 1.6 times 10 to the minus 5. You know how to get that. With Kw, you know. Kw equals Kb, Ka times Kb for a conjugate, Bronsted-Lowry conjugate acid-base pair. You know how to get that. I repeat the question. Is this solution acidic, basic, or neutral?
Basic.
I got to vote for basic. What say you, the rest of you? Acidic, basic, neutral. I got a system which initially contains ammonium ion as the acid, main acid, and cyanide ion as the main base. What's Ka ammonium ion? 5.6 times 10 to the minus 10. You're looking at the information in the table. Kb cyanide is calculable from KaHCN and Kw. And it computes to be 1.6 times 10 to the minus 5. So I repeat, is the system acidic, basic, or neutral?
Basic.
Basic. Kb cyanide is a heck of a lot bigger than Ka ammonium ion. This kind of stuff I want to know before I start doing arithmetic. System is basic. All right? Now then, one remaining issue. Why is it that the molarities of HCN and ammonia are not equal for this system at equilibrium? Right here. That's why for this system, you've got to pay attention to material balance and charge balance if you want to get the hydronium ion concentration. That I overlooked when I did this the first time. But I learned. Good for me. Now I want you to learn. So it's good for you. Why is it that those molarities are not equal at equilibrium? Go ahead.
Because it could be reacting with hydroxide or hydronium.
Hydroxide or hydronium?
Isn't that the material balance?
Wait a minute.
Or water.
Water, you betcha. Water's the main thing which with all these ingredients will react. That's what Ka or Kb reflects, doesn't it? Ka, a measure of the strength of the acid to protonate water, and Kb, a measure of the strength of a base to deprotonate water. Right? One's a hydronium ion making reaction, the other one's a hydroxide ion making reaction. Hey. So therein lies the rub of the grin. If I look at these two principal species, and as we've already recognized, well, let's put this down. This thing is a whole lot stronger base than this is an acid. Sounds like double talk, doesn't it? What I said is that the ability of cyanide to react with water is much greater than the ability of ammonium ion to react with water. That's why we recognize this system as basic. And that's why the equilibrium molarities of HCN and ammonia can't be equal. Because when we pay attention to the reactions which account for system pH, we realize there's a big difference in their abilities to do this. Main species, ammonium ion, cyanide ion. The cyanide ion will react to a larger extent with ammonia. With water, than will ammonium ion react with water. Same idea here. Ammonia will react to a much larger extent with water than HCN will react with water. Well then, the reaction of ammonia with water is going to remove ammonia from the system more effectively than the reaction of HCN with water. Because Kb this is a whole lot bigger than Ka this. Now then, statement. Take a look at bonus quiz 2, spring 13. It's on Sakai for your examination as you see fit. And you will see how this problem is in fact solved. But we've told you all the stuff now upon which the solution depends. That's what counts. Knowing what the solution depends on, rather than the solution itself. Okay, enough on that. We go now to the last issue raised by Chapter 18 stuff, which really is a takeoff on what we're doing with a case like this, or a case like the aluminum sulfate solution. pH calc, hydronium ion concentration calc, who cares? Or a solution in which principal, Bl, Bronsted-Lowry, AB, acid base, EQ, reaction. Does not involve hydronium ion or hydroxide. Hey, like that case, the aluminum sulfate solution. Example. We're interested in calculating the hydronium ion concentration for 0.10 molar sodium bicarb solution. This, of course, is the example considered specifically in the notes, but it is a challenging consideration. So we'll talk about this system, and you can take advantage of the fact that what we're now going to talk about is already in the notes. So you can pay attention to what we're talking about directly, and then use the notes for reading, study, doing what's necessary to make sure you understand what's going on. Earlier on in Chapter 18, after writing a principal system inventory for sodium bicarb solution, we found out that the strongest acid in the system is bicarbine itself, and the strongest base in the system is, in fact, bicarbine itself. So here's our main acid-base equilibrium reaction. Hydrated CO2 and carbonate ion as the products. And we see that this reaction corresponds to this condition. Here's the main reaction, but doesn't involve hydronium ion or hydroxide ion. Tell me, you got any sodium bicarb at home? Baking soda. You got some baking soda at home? Buy some. Inviting you to dip into your penny bag. Buy some. Do some chemistry with it. Brush the teeth with it. But as we mentioned earlier on, I would suggest strongly that you don't attempt to deodorize your refrigerator with an open box of sodium bicarb. It may well work, but I suggest more to the point is to go into the refrigerator and get rid of the rotten stuff. The stuff that's causing the stink. Rather than trying to absorb the stink with sodium bicarb, given that the stink will continue to be generated as long as the rotting stuff is present in the refrigerator. If you at home make a water solution of sodium bicarb, which you need do only by taking some of your baking soda, putting it in water, dissolving it, and putting it in a pan on the stove and heating it up. If you make sodium bicarb solution at home and heat this solution on the stove, what do you think you're going to see? Do you think this reaction is exo or endo? Because if it's exo, heating will make it go this way. Does this reaction go left or right by heating? Exo or endo? We talked about this earlier on. I wonder if you remember it. Determination of whether or not a Bronsted-Lowry acid-base reaction is exo or endo depends on looking at the reacting acid base with the product acid base and asking, between which reacting pair do I observe the greater tendency for H+ exchange? And that leads to determining reaction extent, doesn't it? What is the extent of this reaction? Large or small? Small. Acid. Could be the base, who knows? Base. Look at the acid-base table. Ka bicarb, 4.8 times 10 to minus 11. Ka for the product acid, 4.2 times 10 to minus 7. Hey, well, hydrated CO2 is a lot stronger acid. And if you compare Kb carbonate to that, you'll see the same thing. Kb carbonate's a lot bigger than Kb bicarb. That means the extent of this reaction as written is quite small. And it also means the reaction as written is endo, because the tendency for H+ exchange will always be greater between the stronger acid and stronger base, here rather than here. That's why heating this baby makes it go. So you're back at home, you got this solution, you're cooking it. What do you think you might see? Bubbles. Because you're going to shove this to this, and this readily decomposes because it's not very stable, and bubbles. So if you take your kid brother or kid sister or niece or whatever the heck, and you do this at home, you can now explain it. How about that? Why the bubbles? I mean, a little kid looks up to you and says, you're in college studying chemistry, tell me what's going on here. Now you can do it. That's pretty good. Fun, isn't it? But back to getting the hydronium ion molarity for this system. Can't do it with this reaction. Then I have hydroxide or hydronium ion in it. But I can do it with this. By definition, what's K for this reaction?
4.8 times.
I don't want a number. I want a definition.
What's the rate of the product?
I don't want to know anything about rates. There's no kinetics going on here. No rates, nothing. What?
Products of a reactant.
By definition, this is Ka for HCO3 minus. That's what we're looking for. Right? Because here's bicarb reacting with water. So immediately that tells us it's a Ka or a Kb. And I see hydronium ion product, Ka. Or I can look at this. Which by definition is Kb bicarb. I just want to keep us in touch with what the heck these equilibrium reactions mean. All right? Now then, perhaps you'll recall, because we focused on this earlier on in the term, Ka is 4.8 times 10 to the minus 11. Kb is 2.4 times 10 to the minus 8. With those data before us, we can answer the question, is bicarb solution acidic, basic, or neutral? Basic, because Kb is bigger than Ka, which means the ability of bicarb to steal H plus from water is better than its ability to give H plus to water. Behaves more strongly as a base than it does an acid. All right? Will it be mildly or strongly basic? Mildly. Hey, these K values are tiny. The reaction extents are pretty daggone small. Now a question. Tell me, how does the extent of this reaction, how does the extent of this reaction compare to the extents of either of these? Well, we can start by knowing that the extent of this reaction exceeds the extent of this reaction. K values tell us that. So how will the K value of this compare to this number? Let's write it down. Let's call this reaction, I don't know, A. Ka versus 2.4 times 10 to the minus 8. The value for K versus, how are these values going to compare?
I think the K is going to be greater.
You think it is. And tell me why you think that way.
I believe that because I was comparing the values of the Kb for, where I was looking at the parts in the hydroxide. The hydroxide is going to have a much higher Kb than.
Hydroxide has a much higher Kb.
I was comparing the parts.
I agree with that, but
Like the difference between hydroxide and water is
I think you're getting off the track. Somebody else.
Kb by.
I want to know how K for that reaction, magnitude-wise, compares to 2.4 times 10 to the minus 8. All right. It's greater than 2.4 times 10 to the minus 8. Tell me why.
You think that with respect to KW?
Nope.
Is it amphoteric?
It.
Is HSCO2 minus amphoteric?
Yes.
It's acting as an capacitor of base, so it would be.
Oh, I agree, it's amphoteric, but what's that got to do with the extent of this reaction? Look. Here's the reaction equation corresponding to KB, isn't it? In either of these cases, bicarb ion is a reacting acid. Pardon me, base. For KB, okay? Here's acid bicarb, here's base bicarb. Well then, by default, for this system, what's the reacting acid? Good. You tell me, bicarb ion, are you going to more effectively, in reacting as a base, deprotonate water or deprotonate bicarb ion? Which one of these do you more readily deprotonate? Bicarb or water? Why?
It's a stronger acid.
Yes! By golly. You see this? Bicarb is a stronger acid than water, a good deal stronger. Right? I'm just asking, pay attention to this information. Let it talk to you. You got to know what it means. Otherwise, it's just a sea of numbers giving you massive headaches. We don't want that. So the K value for this is a lot bigger than 2.4 times 10 to minus 8. Because this baby is a much stronger acid than water. It guarantees the extent of this far exceeds the extent of that. Now then, why were we of a mind to consider this? Well now, I'll ask a question. Given that we can use either of these to calculate system hydronium ion concentration, because either of these pay attention to source of hydronium ion or hydroxide ion, if it's handled on pH, and involve principal system components, bicarb ion and water specifically. Sodium ion is also in here. Who gives a damn? It's the spectator at the football game. And when textbooks learn that spectator ions do not belong in reaction equations, because they don't react, they'll start to get better. Until they learn that, they can burn them damn books. Because they don't know how to do system inventories. Okay? So I'll use this one, because it gives a handle directly on hydronium ion. Okay? 4.8 times 10 to minus 11. There's the K expression. Now comes the $64 question, which, if you remember to what we talked about regarding this system, the ammonium cyanide system, you'll know what the answer is to this. For this expression, is it true, yes or no, that the hydronium ion molarity and the carbonate molarity are the same? For this system, the hydronium ion molarity, carbonate molarity, are they equal to each other? Yes or no? The answer is no, they are not. Now then, why are they not equal? And which one is larger? Why are they not equal? Did we not recognize that this is the main acid-base equilibrium in this system? Right? And this system produces carbonate, doesn't it? But it doesn't produce hydronium ion. Now this system also produces carbonate. So how many reactions in this system produce carbonate? Two. And one of them is the main reaction in the system. But only one of the reactions produces hydronium ion. That tells us why carbonate and hydronium ion molarities can't be the same, just like the molarity of this and the molarity of this. Can the molarity of this and the molarity of this be the same? Absolutely not. You got to keep this in mind when you start wrestling with these equilibrium constants, okay? Well then, if these are not the same, which one is bigger? Which one?
CO3. CO3 2 minus.
Have we not found there are two sources of this? And one of the sources is the largest extent reaction in the system? Between these two, which molarity is larger? H2CO3 because?
There's two reactions that has
Two sources of this, right? But only one source of this. And now you've recognized the complications involved with wrestling with this system. So what I expect Professor Mosen to start with tomorrow is, what further considerations do we need to make for this system to calculate the hydronium ion concentration? What do you think these considerations will be? You think this might be one of them? You think this might be one of them? Do you think for this system, after I write the charge balance equation, I can set it equal to a charge sum? What is the charge sum? What's the charge sum for this system? Your eyes are in the wrong place.
going back to point one.
Is this the label on the bottle? Does this system contain sodium ion? And the sodium ion molarity is? Now, besides sodium ion, in this system, what's the other positive ion? There are only two of them in here. There's your two positive ions in the system, right? And we know this is 0.10, right? How does the concentration for this compare to 0.10?
Incredibly small.
Incredibly smaller. Why?
Because it's a basic.
This system is basic, damn it. This is smaller than 1 times 10 to minus 7. If I add that to this, I'm not changing this. Bingo, there's the charge sum. Pay attention to the chemistry of the system, and it works. And if you don't, it won't. Oh! All right. Now, my apologies, I don't know yet who you are, but Yoder. Yang. If I mispronounce your name, just holler. Williams, Catherine. Whitaker. White. Urs. Tringali. Salandros. Over there. Poe. Lundgren. It's pretty good. Long. Lee, Andrew. Knowlton. Kalanda Hill. Jones. Pretty good. Johnson. Hendry. My golly. Tiny writing.
Giara?
Is this you?
Yes.
Can you write a little bit larger? Godoy. Let's see this one moment. Okay. Glenn. Fernandez. Dodge. Creech. Good. Chook. Charleston. Bryant. Bryant. You are Mr. Bryant? Barrera. Annabelle. And Allen. I miss anybody? Andrew. What's your last name? You got to give me the last name. Okay. Now then, as I told you, there are over 340 points earnable on this exam. But frankly, this stuff is tough. It's made on the order of 200 or more. Hey, you did pretty good. Now then, for those of you who didn't fare well, in each and every exam, and quizzes if we have them, I purposely build a whole bunch of earnable extra credit into that because this stuff is tough. And I want to give you every opportunity to show me that you're getting at it. It takes time. I'm sympathetic with you, believe me. But I sincerely want you to learn this stuff. So if you didn't fare well on this, keep in mind you got all kinds of opportunity to pull yourself up. I can tell you for a fact that a whole bunch of people in previous Summer 2046 classes, which I ran, got bombed on the first exam, or bombed the first exam, however you want to, and made A's. Because they wised up. They recognized their responsibilities. Because now you know, I ain't kidding, and I mean that's it. No soft touch here. It ain't me, it's chemistry. I'm letting you see what chemistry's really like. You know, so you can tell all those people who run around this campus talk about how tough Horvath is. That's a bunch of baloney. Horvath just has the gall to show you to what chemistry really is. It's chemistry that's really tough. And that's why these idiots who sell you programs are going to make a master of chemistry out of you. If those programs worked, I'd have bought them a long time ago. And so would everybody else who wants this stuff. Okay? Now then, I will post a key. Take a look at it. First, in the event that you have questions, consult the key first. Secondly, if you still have questions, let me write this down. Page 1 for this exam graded by Aya. Page 2, Lynn or you? You did? Okay. Lynn Pham. Page 3, to win. CDs. And if after these interactions, if you're still not satisfied, you still got questions, then see me. Or you can see Mr. Mosen. Now, of course, you won't be able to see me till I return, but if there's any problems or difficulties and we made a mistake, I assure you I will fix it. I don't want you at all ever to be penalized by goofs that I make. And I made a couple on this exam. I'm not surprised. This stuff is tough. I don't escape from that factor at all. So, carry on.